was where we stopped in the last class. We did talk about how the kinetic energy and the potential energy are going to change as a function of time as well as a function of position. Remember, your sum of kinetic energy and potential energy is always going to be a constant. Even though the portion of potential energy and kinetic energy can vary from one location to another location, but their sum is always going to be remaining constant, and we already derived that constant to be equal to 1 by 2 k a square, where a is the amplitude and k is your spring constant. Now if you put it in the figure form, here you are sitting at the extreme in the first figure. So your energy is totally in the form of potential energy and your kinetic energy is zero because your velocity is zero at these points. If you come to the equilibrium position where your velocity is maximum, your total energy is basically kinetic energy. The potential energy which is equal to 1 by 2 k x square, and since your x is equal to 0, so your potential energy is 0. If you go to the other extreme where x is equal to a, again your total energy is in the form of potential energy. But if you are in between these 3 points here, which are your two extremes and one equilibrium position, then your energy is going to be sum of kinetic energy and the potential energy. Which one of them would be more and which one of them would be less, that would depend on the location. But your sum is going to be a part kinetic energy and a part of it will be potential energy. And if you add both of them, that would always be equal to 1 by 2 k a square. Now let's talk about the total energy. Your total energy we said is equal to kinetic energy plus potential energy. This derivation is basically to get the expression for velocity at any location during the oscillation. So your total energy is equal to 1 by 2 k a square. Kinetic energy is 1 by 2 mv square, and your potential energy is given by this expression here, 1 by 2 k x square. You can rearrange the terms here, bring this term on one side and the other terms on the other side. Am I still audible?
Yes, ma'am, you are audible.
Okay. So your 1 by 2 mv square, or basically your kinetic energy, is equal to total energy minus potential energy. 1 by 2 is common. You can cancel it out from all the three terms, and you can say that your mv square is equal to this expression over here. K you can take common out, and hence your velocity will be equal to the square root of this whole term. K over m was equal to omega square. You can take omega out, and your velocity will be equal to plus minus omega square root of a square minus x square. Now, if you talk about the maximum value of velocity, right? Your maximum value of velocity will be when your x is minimum, and the minimum value of x is equal to 0, right? And hence your maximum velocity is equal to omega a, and we derived that when we said that your x is equal to a cos omega t plus phi, and then we said that your velocity will be equal to minus a omega sine omega t plus phi. At that point also we said that your maximum velocity will be equal to a omega, because your maximum value of sine is equal to 1. So from there also we came to the same conclusion, and from here also we can prove that the maximum value of velocity would be equal to omega a. But if you want to calculate your velocity at any point, then this would be your expression. You just need to plug in the value of x and you can get what would be the value of velocity at any point during your oscillation. Now let's talk about the second case of this block spring system, which is what if it's rather than being horizontal, it's vertical in position. What would happen in that case? So if you have a spring which is in vertical position over here, and you attach a mass to this spring, the spring is going to expand and eventually your mass is going to come to some equilibrium position. Now if I'm going to show the name of the annotators. So now with respect to this equilibrium position, if you pull this mass, remember this is going to be now your equilibrium position here. Now with respect to this equilibrium position, if you pull this mass down and then release this mass, it is going to execute the simple harmonic motion. And with respect to this equilibrium position, this simple harmonic oscillation is going to be exactly similar to your horizontal spring mass case. The restoring force, everything, the kinetic energy, the potential energy, the velocity, everything, the expressions that we derived for the horizontal, they will be applicable here also. Now one could argue what would happen to the gravity. The effect of gravity disappears in this case, or basically it is cancelled out. That would be the rather right term. How is that cancelled out? There is a numerical based on this in your tutorial. Ask your TA or faculty member to prove that if you don't know how does that happen, and if you are still not able to get the answer, then message me. We'll get back to this derivation and then we'll prove that how the effect of gravity is going to disappear in this case, and how if you take this position as your equilibrium position, how you can treat it exactly similar to a horizontal vertical spring case. Now coming to the next case here, the next one is the pendulum here. Pendulum also executes simple harmonic oscillation. One of the conditions or the assumptions of simple harmonic oscillation is that you say that your displacement from the equilibrium position is not extremely large. You make the assumption that your displacement from equilibrium position is small. In the case of pendulum, you have already again probably done this expression over here. Let's say L is the length of the pendulum over here, the thread through which your mass is attached, and then you pull it to one side and then you release it. The mass is going to act in the downward direction. This angle would be equal to this angle over here because this is a straight line, and then these two lines are parallel to each other. You can break this force into two components, the mg cos theta and mg sin theta. Mg cos theta is equal to tension here, and mg sin theta basically acts as your restoring force, which would try to bring this mass back to its equilibrium position. Now, as we said before that, in the case of simple harmonic motions, we assume that your displacement from equilibrium position is not extremely large. So in that case, I can treat this as a triangle here. Conditionally, again, if this mass is not moved as at a very large distance from its equilibrium position, if this arc length is small, you can treat it as a straight line approximately. Now, in that case, this distance over here, which is denoted by S over L, would be equal to sine theta. And if I'm saying that we haven't moved this object very far from its equilibrium position, that means your theta is going to be small. If your theta is small, then you can approximate sine theta with theta, and you can say that your S will be equal to L theta. Now, we said that your restoring force here would be equal to minus mg sine theta, which would try to bring it back to its equilibrium position over here. F is equal to mass into acceleration. Your acceleration is to second time derivative of displacement. So I can write your force in this expression over here. M times d2s over dt. Remember, S is this distance over here. Is equal to, again, we are saying that your theta is small because your displacement is small. So you can approximate sine theta with theta here. Plug in the value of S from here, which is equal to L theta. L is a constant because L is the length of the string through which your mass is attached. So you can take L out here, you will get d2 theta over dt, right? And here, in this side, M will cancel M, you will have g theta over L here. So this would be your equation here. If you compare this equation with your SHM motion or the block spring equation that we derived earlier, here you can draw some conclusions from here. You can say that your omega square, which was equal to k over m in the previous case, in this case your omega square would be equal to g over l. That means your omega would be square root of g over l. and hence you can calculate your time period. Your time period is defined as 2 pi by omega. Plug in the value of omega here, you will get this expression for time period, which you are familiar with very well. Now, if you look at the time period over here, this time period depends on the length, this time period depends on the gravity. It is independent of the amplitude, which basically means that it does not matter if you pull it aside by a small amount, or you pull it by, let's say, by 1 mm, or you pull it by 5 mm. It is independent of that. Your time period will be independent of your amplitude. And we did see that in the case of a block spring system also. In that case also, your time period was independent of the amplitude. Now we are going to move to the next topic, which is your electrical oscillator. This oscillator is your equivalent to an ideal simple harmonic mechanical oscillator, which we discussed. This will be, which basically means that your LC circuit is an electrical equivalent to a block mass spring system in which your friction is zero. In the LC circuit also, we are going to assume that there is no resistance present in the wire whatsoever. Again, this is an ideal case. In reality, it does not happen. We'll talk about more realistic cases also, where we are going to take resistances also into account here. So in this case, we are going to assume that initially your capacitor was charged to its full capacity, and at time t is equal to 0, we close the switch here. What would happen? You have already done this expression for the derivation, right? Your charge as well as current is going to oscillate between some maximum positive and the negative value. You know that we are assuming an ideal case. That means there are no resistance present. So the charge and the current are going to oscillate for an infinite amount of time, because there is no dissipation of energy in the form of heat energy, which is what usually happens if the resistances are present in the circuit. Now, if you want to compare this LC circuit with the block mass case here, let's say that initially your capacitor was fully charged to an amount equal to Q maximum. At time t is equal to 0, there was no current in the circuit. You know that the energy that is stored in the capacitor, it is in the form of electrical energy. And the energy that is stored in the inductor, that is in the form of magnetic energy. And hence in this circuit, your energy is going to oscillate in the form of electrical energy and the magnetic energy. But the sum of these two terms is always again going to remain the constant, right? So here, if you compare this with your block spring case here, let's say that initially your capacitor was fully charged here. This will correspond to the case when you have stretched your mass to the one of the extremes here. Now, what would happen at time t is equal to t by 4? Your capacitor will be fully discharged, and all the energy that is present in the circuit will be in the form of magnetic energy in the inductor. Remember, your inductor produces an induced EMF, right? And that is directly related to the rate of change of flux here. So at time t is equal to 1/4 of the cycle, which is equivalent to your mass coming back to its equilibrium position, the energy is stored totally in the inductor. The charge on the capacitor is 0. That means there is no electrical energy in the circuit at this point. Now, if you go to the time, that is equal to the half time period, which is this case here. In this case, this is equivalent to your mass moving to the another extreme, which is equal to x is equal to minus a. Now your capacitor will be charged again, but with opposite polarity. Initially, you had plus q charge here and minus q charge here. But now the polarity of the charge of the capacitor is going to be reversed. You will have plus q on the lower plate and you will have minus q on the upper plate at half time period. Again, if you go to t is equal to 3/4 of your time cycle, that would be equivalent to this mass coming back to its equilibrium position. Again, your capacitor will be fully discharged and Your energy will be totally in the inductor in the form of magnetic energy. Go to
What?
the
Neeraj
time.
Bansal, sorry ma'am, Neeraj Bansal wants you to repeat one LC circuit.
Uh, can you repeat again?
LC circuit, Neeraj Bansal wants you to repeat this one LC circuit.
Okay. This LC circuit, we are assuming it to be an ideal LC circuit. That means there are no resistances present in the circuit. We are assuming that initially your capacitor was fully charged, and that maximum value of charge we are assuming to be equal to Q max. And at time t is equal to 0, we are saying that we are closing the switch here. So your energy is going to oscillate between a capacitor and inductor. You know that capacitor stores energy in the form of electrical energy. Inductor stores energy in the form of magnetic energy. And hence your energy is going to oscillate between these two components. Your charge and current will see that both of them are going to follow a sinusoidal pattern with respect to time. Energy is going to remain constant. The reason being that we are assuming that there are no resistance, hence there are no ways in which your energy can be dissipated in this circuit. Now coming to back to this circuit over here, let me erase this. Now coming back to the circuit over here, as we said before, at time t is equal to 0, we are assuming that our capacitor is fully charged here. Let's say this was the way our capacitor was charged at time t is equal to 0. There was no current in the circuit. This would be basically equivalent to your block spring case when you have stretched your mass to the extreme from its equilibrium position. Now at time t is equal to 1/4 of the cycle, what would happen is that your capacitor will going to, at from here to here, your capacitor will start discharging, right? At time t is equal to 1/4 of the cycle, your capacitor would have fully discharged. You will have the maximum current in the circuit, and your total energy of the circuit will be stored inside this inductor. Now, this would be equivalent to your mass coming back to its equilibrium position here. If you go to the time period, which is equal to 1/2 of your complete cycle, in that case, what would happen is that your inductor will start, there will be a flow of the current again, and this time your capacitor will be charged back, but it will be charged with opposite polarity. But the amount of charge is going to remain the same, because we are saying that there is no dissipation of energy here. And this would be basically equivalent to your mass being stretched to the other extreme. That is equal to x is equal to minus a here. If you further go to time is equal to 3/4 of the cycle, in that case, what would happen is that your mass here will come back to its equilibrium position here. And in this circuit, this will be basically equivalent to this capacitor again being discharged completely, and your total energy being stored in the form of magnetic inside the inductor. Go back to time t is equal to t, and you will come back to the initial state when your capacitor is going to charge once again with the same polarity as it was charged at time t is equal to 0, and there will be no current in the inductor. So this is basic equivalence of your block spring case and LC circuit, if you want to get some kind of equivalence between these two circuits here. If you look at this circuit over here, you can say that the energy that is stored in the capacitor is basically equivalent to the potential energy in the block spring case. And the energy that is stored inside the inductor, that is equal to the kinetic energy in block spring case. The maximum energy inside the capacitor can store energy equal to Q square over 2C. If you talk about the maximum energy that can be stored inside this capacitor, since we are saying that the charge, maximum value of charge could be Q max, so the maximum energy would be equal to Q max square over 2C, which would be your energy at time t is equal to 0, and this is also equal to the total energy. because there is no energy stored in the inductor at this point. Similarly, at t is equal to 1 by 4th of the cycle, when we said that your all of the energy is stored in the inductor, your energy would be equal to 1 by 2 L I max square. I max represents your maximum current in the circuit, and this is again equal to your total energy. At this point, there is no energy stored in the capacitor. Hence, you can basically say that your total energy would be either equal to Q max square over 2C, or it can be either equal to 1 by 2 L I max square. At any other point apart from these two extremes, your energy will be sum of both the terms. The term due to energy storage in the capacitor and the term due to energy in the inductor. So if you want to talk about energy at any point, then your energy will be equal to Q square over 2C plus 1 by 2 Li square, where Q is the charge on the capacitor at that point of time and I is the current that is flowing in the circuit. If you look here, we have just chosen the time, which basically represents some standard fraction of the cycle, which is equal to 1 by 4th of the cycle, half of the cycle, 3 by 4th of the cycle, right? But if you take any time period in between these 2 points here, your energy will be sum of both of the terms, where remember now I'm not writing Q max here, I'm talking about the charge, whatever is the charge that is present in the capacitor at that point of time, and I represents the current that is flowing through the circuit at that point of time, and that we'll see that both your charge as well as current are going to be sinusoidal functions. They are going to depend on the time here. Now, this is your LC circuit. You have a certain amount of charge on the capacitor, which let's say is Q over C. You have a certain amount of voltage across the capacitor, and let's say that the charge on the capacitor is given by Q. So if charge is Q, then your voltage will be given by Q over C. The induced EMF that is generated on the inductor, you know that is given by L di by dt, right? That is your induced EMF on the inductor. Now, if you apply Kirchhoff's second law or Kirchhoff's voltage law, the sum of all the voltages in this circuit should be equal to 0. So that means if I have only these two voltages present in this circuit, the sum of these two terms should be equal to 0. And you know the Kirchhoff's voltage law, that you either go from plus to minus. From here, you take the same sign. If you are going from plus to minus here, and then you are going from plus to minus here. So the signs of these two terms will be same. Either you can take both of them plus, or you can take both of them minus, whichever way you want. Now you know that I is equal to dq by dt. If I put that value of I here, that means your di by dt would be equal to d2q over dt2. And that's what has been done in the next step over here. If you further move the L term from here to here, because I would like to get this in a similar form as was in the case of a block spring case. Remember, in the case of block spring case, we had something d2 over dt2 plus k over m x is equal to 0. So I would like this expression or this equation also to be in the same form. So this is our equation for LC circuit. This was your equation for a block spring case, right? We said that k over m was equal to omega square. If we know that what was our solution for x, based on the similar argument, I can say that my solution, because this is a second order differential equation in charge, so I can say that my charge, I should rather write it charge as a function of time, because this is not constant. It's going to vary as a function of time. So your charge would be equal to Q max cos omega t plus phi. For this equation, we remember said that your xt is equal to a cos of omega t plus phi, where we said that a is the amplitude, omega is the angular frequency, and phi is the phase constant or the phase angle. Based on the similar logic, for this equation, I can write it in this form also, where Q max corresponds to your maximum charge here. If you talk about omega in this case, your omega square is equal to 1 over LC. If you compare it with this circuit, where your omega square was equal to K over M, here your omega square is equal to 1 over LC. And you can prove that your omega would be equal to 1 over square root of LC. Simply take this value of Q, plug it into this expression over here. And you will see that you can prove that your omega square is equal to 1 over LC. This omega is called as natural or resonance frequency of the LC circuit. This means that this represents your frequency with which your charge and current are going to oscillate in the circuit. Right? Now, Q max represents your maximum charge of the capacitor. The phase angle here, we can decide the phase angle from initial conditions, as we did in the case of Bloch spring case also, right? Remember, in the case of Bloch spring, we derived the expression when it can be a sine function and when it can be a cosine function. If you know the initial conditions, and by saying the initial conditions, I mean to say that if you know what was the charge, what was the current at time t is equal to 0, right? Then you can know what would be your phi here. Let's say that here in this particular scenario, we said that at time t is equal to 0, your capacitor was fully charged and the current flowing in the circuit was equal to 0. As was in the case of Bloch spring system, it's the similar. You do not have to start at time t is equal to 0, Q being equal to Q max and I being 0. Someone can say that I don't want to start my clock at that time. I want to start my clock at the time when my current in the circuit is maximum and charge is equal to 0 on the capacitor. And that is absolutely fine. Only problem in that case would be, or the only change, not the problem, the only change in your solution would be that the phi would be different in that case. Because in that case, let's say when you are saying that at time t is equal to 0, your I was equal to I max and your Q was equal to 0. Then whatever we are going to do now to determine the phi, you have to do it for these values. And whatever solutions you are going to get, that will be absolutely fine. So there is nothing wrong with that. One can always start his or her clock at any point of time. There is nothing wrong with that. The phase factor or the phase angle that has been introduced actually takes that into account. The time at which different persons might start their clock for the measurement of the time period or the frequency or whatever they are measuring. It takes that into account, this phase constant or the phase angle. That is the whole purpose of this phase, that the initial condition might be different depending on the person here. So in our case, let's say that this was our charge, I is equal to dq by dt. That would be equal to minus omega q max sine omega t plus phi. Now I'm saying that this term here, omega q max is equal to I max. We can prove that. Look at this expression over here. We said that your total energy is equal to Q max square over 2C. And this could also be equal to 1 by 2 L I max square. Your 2 will cancel from here. You can say that your I max square is equal to Q max square over LC. Or you can say that your I max square is equal to Q max square 1 upon LC. We prove that is equal to omega square. So one can say that your I max would be equal to omega times Q max. And that's what has been put here. I have said that omega times Q max is equal to your maximum value of the current in the circuit here. Now, at time t is equal to 0, we are starting our clock at the point when the charge on the capacitor is maximum and your current is equal to 0. So, in this case, what would happen is that if you talk about equation number 6 and equation number 5, in equation number 5, I'm saying that you will have Q max cosine of, I'm saying time t is equal to 0, so you'll have phi here. And at time t is equal to 0, your charge was equal to the maximum charge. So this becomes equal to 1. So that means your phi is equal to 0 in this case. If you talk about equation number 6, we said that your current is equal to 0 at time t is equal to 0. So your this term is equal to 0. You will have minus I max sine phi, which is also proving the same thing, that your phi is equal to 0 in this case. So if you are starting your clock at time when your charge on the capacitor was maximum and when there was no current in the circuit, in that case your phi would be equal to 0. But if you take the another case, that at time t is equal to 0, your current was maximum and your charge was 0, your phi would be different in that case. And I would like you to do that by yourself. Now, this is your charge now, and this is your current now. If you want to plot your charge and current as a function of time here, so it has been shown that at time t is equal to 0, your charge would be equal to the maximum charge. At time, I can further write it as omega is 2 pi by t multiplied by t. If you take t is equal to t by 4, t will cancel, you will have cos pi by 2, and cosine of pi by 2 is equal to 0. So you will have your charge being equal to 0. If you put t is equal to t by 2, you will have cos of pi, and that is equal to minus 1, and you will have minus q max as the charge, and so on. Similarly, you can do the same thing for current also. At time t is equal to 0, your current is 0. At time t is equal to t by 4, this is t. If you put it as t by 4, your time will cancel. You will have sine pi by 2. Sine pi by 2 is plus 1, and you will get minus I max. So this is what happens at time t is equal to t by 4. Your current is equal to minus I max. And similarly, you can plug in the value of t by 2 or 3t by 4 and t, what would happen at the current in this case. But if you look both at the charge as well as at the current, both of them are sinusoidal in nature, and your charge oscillates between two extremes, q max and minus q max. Similarly, your current also oscillates between two extremes, I max and minus I max. If you talk about the total energy, we did say that if your energy is stored totally in the capacitor, your energy is equal to q max square over 2c. If your energy is totally in the inductor, this is equal to 1 by 2 L I max square. But what if we want to calculate the energy at any random point of time? And I would like to prove that my total energy at any random point of time is also equal to constant. I would like to prove that this term is equal to q max square over 2c, and this is also equal to 1 by 2 L I max square. You can prove this to be equal to either of these terms here. Here I am proving that this is equal to this term here. Simply reverse the values that I am plugging in here, and you can prove that this would be equal to 1 by 2 L I max square. Do that by yourself. And if you face any problem, let me know. Okay, so let's start with this expression over here. You have q square over 2c plus 1 by 2 Li square. We said that your q is equal to q max cosine of omega t. I'm not writing it as a function of time because I'm assuming that it is obvious that you are saying you are familiar, or you already know that your charge and your current are always a function of time. Similarly, your I would be equal to minus omega q max sine omega t. And we did prove that omega times q max is equal to I max sine times omega t. This would be your expression. This is equal to your I max. Plug in the value of q and I into this here. You will get your q square will be equal to q max square cos square omega t, 2c as it is, plus 1 by 2 L. Plug in the value of I. You will get omega square Q max square sine square omega t. So you will have omega square Q max square sine square omega t. This is your value of I square. From here, go to the next step. The first term has been taken as it is. Omega square is equal to 1 over LC, right? And you will have Q max square sine square omega t. LL will cancel each other here. You have 1 upon 2C here. You have 2C here. Q max square is also common here in both of the expressions. You can take Q max square over 2C common here. You will be left with cos square omega t plus sine square omega t, which is equal to 1. And hence you can prove that this is equal to Q max square over 2C. Again, rather than putting the value of current in terms of the charge, do it other way around. Put the value of Q max in terms of I max, and you can prove that this is equal to 1 by 2 L I max square also. Again, do that yourself. Please try to do it. From here, we have proved that at any point of time, your total energy, not only at the fixed intervals that we did in the figure from the figures conveniently, at any random point of time, your total energy, which is going to be sum of the energy stored in the capacitor and inductor, is going to remain the constant. Because your Q max is constant, your capacitance is also constant. Or you can say that your inductor value is constant and your I max is also constant here. If you talk about the energy stored in capacitor and inductor as a function of time here, you have something as a cos square omega t. Let's see, at time t is equal to 0, your total energy was in the capacitor. Your cos square would be equal to 1, right? At time t is equal to t by 4, again you will have cos pi by 2 here, and that would be basically equal to 0. If you go to t by 2, plug in the value here again, 2 pi by t multiplied by t by 2. They will cancel each other out. You have cosine of pi, which is minus 1. Minus 1 square will be equal to plus 1. So your energy would be again maximum here. It will be equal to Q max square over 2C. Similarly, if you talk about inductor, at time t is equal to 0, there was no current flowing in the circuit, and hence your energy stored in the inductor is 0. At time t is equal to t by 4, put the value of here, this will cancel. You have sine pi by 2. That is the maximum value of sine 1. You will have 1 by 2 L I max square, and hence your energy is equal to this term. And at t by 2, your energy would be minimum. So whenever the energy stored in the capacitor is maximum, energy in the inductor is going to be minimum, and vice versa. At any other point, if you take sum of these two curves over here, if I can plot this curve also on the same graph, it would look something like this. The energy of the inductor. If you take sum of these two graphs, it is always going to remain the constant, which is the total energy stored in the circuit. And I think I'll stop here. I can take a couple of doubts since no one is here so far. बच्चे जय हिंद आपस में just make some another group to do that. Don't do that here. Yes, these PPTs are already available on LMS.
Ma'am, can I allow them to unmute themselves to ask the few questions?
Yes, that. No one is here. I'm supposed to sign out, but let's see if we can take a couple of questions here.
You can ask your question.
Piyush, you has doubts. You raised your hand at some point of time. Akshit, you can ask your question.
मैम जो बिल्कुल फर्स्ट डाउट लिया था अपना जिसमें द ऑब्जेक्ट वाज इन द मिडल एंड द वेयर विल बी द एक्सेलरेशन देन द फोर्स वाज टुवर्ड्स द इक्विलिब्रियम पोजीशन
The equilibrium, the force is zero, and hence there is no acceleration at that point. Acceleration would be equal to zero, right? You are saying your force is equal to minus kx. If your x is equal to zero, there is no force, and hence no acceleration.
नो मैम व्हेन द एक्स वाज इन द मिडल मैम
Yes,
कैन यू प्लीज ड्रॉ दैट अगेन
when x is in the middle, right?
yes between the highest amplitude and the zero equilibrium
Oh,
position
at this point, you are
yes ma'am
saying,
yes
okay.
ma'am
So
yes ma'am
if you are moving in this direction here, right? So your force is
yes ma'am
acting in this direction. So your object is going to deaccelerate, and it will eventually stop here because there is
yes
a
ma'am
continuous application of a deaccelerating force. So your velocity would become zero at this point here. Now, in the other case, if you are saying that your object is moving in this direction, your force is also acting on the same direction. So your object will be accelerated, and that is the reason you get your maximum velocity at the equilibrium position.
so what will be the direction of the acceleration in this case it will
In
be opposite
No, it's in the same direction. Your object is moving in this direction. Your force is also acting in the same direction,
okay
right? So they are acting in the same direction. It's you can remember it in a very simple way. It's simply that with respect to equilibrium position, if you are sitting at any point in the positive x direction, your force is always going to act in this direction. At this specific point, it does not matter if you are moving in this direction or this direction. Your force is always going to act towards the equilibrium. Similarly, if your object is here, your force is always going to act in this direction. And yeah, at this point, it does not matter if you are moving in this direction or this direction. Your force will always act towards the equilibrium. So in one case, your force will act in direction opposite to the motion. And in another case, your force will act in the same direction as is the direction of object.
okay ma'am
Yes. Vidit. Vidit?
Yeah, actually, ma'am, you said that at the time T by 4, like in the middle between the mean position and the extreme position,
Yeah.
the movement of the block and the acceleration will be in the same direction, right?
Let's go back to that. Here, right?
Yes, ma'am.
Okay. Yes. So with
Yeah,
respect to this, in general, if you are moving in this direction, at any point,
yes,
your force will act in this direction. So
yes, ma'am.
at this specific point, you can be moving in this direction or this direction. It doesn't matter. Your force will always act towards the equilibrium
Yeah,
position.
yes, ma'am. But when we derived the expression for the acceleration and the position, you
Yep.
told that they will be always be in the opposite direction. Means the acceleration was negative and the position was positive.
By that, I meant to say with respect to equilibrium position. I think that word is very important here. If you plug in the value of x here, right? Let's say that this is your x is equal to 0, this is your x is equal to 3, and this is your x is equal to 5. If
Yes,
you
ma'am.
plug in the value of x is equal to 3 here,
Yes, ma'am.
your acceleration is always going to act in this direction because your force is acting in this direction. Again, with respect to this point, it does not matter if your object is moving in this direction or this direction. Your restoring force is always going to act in this direction. So your x is still 3. It doesn't matter if you are moving in this direction or this direction, right?
Yes, ma'am.
And that is what is given in this expression. Okay, so I'm going to sign out. I'm already taken extra time here.